by given mass percents, we can also find empirical formulas. A compound has 55.79% carbon, 7.04% hydrogen, and the rest oxygen. Determine the molecular formula if the molar mass is equal to 86.09 grams per mole. This is important information. The percentages will be able to tell us the empirical formula. We'll do that in a second. From that empirical formula, we can find its mass, the empirical mass, and then we'll compare the molar mass with the empirical masses, because the actual relationship between the molar mass and the empirical mass is going to tell us the relationship between the empirical formula and the molecular formula. So one thing to note is that mass percentages add up to 100. So we can look at the percentage for carbon and the percentage of hydrogen. If we subtract it from 100%, we'll get the percentage of oxygen. Again, since we're looking at formulas here, don't worry too much about sig figs. If you want to practice, that's great. But at the end of the day, you are getting a whole number ratio. From there, what we have with those three percentages is an actual mass number too. Change it to grams. Let's assume that we have 100 grams of compound. We get to assume whatever we want here. If we have percentages, we can assume 1 gram, 10 grams, 100 grams. So 55.7% carbon tells us that out of 100 grams of sample, 55.79 grams of it is carbon. We could convert that to our moles. So we're getting 4.65 moles carbon. Same for hydrogen. Make sure we're not using any diatomics here. This is not a diatomic type question. This isn't a reaction. This is just looking at the elements that are composed in this sample. 6.97 moles each. And we'll take that last one, 37.17 grams of oxygen. 1 mole of oxygen over 15.999 grams. And we get 2.32. So when we look at this again, we divide by the smallest, 2.32, 2.32, 2.32 to try and normalize. And we see C2H3O1. That is the empirical formula. The one could be understood. You don't need that one there. If you wanted to erase it, you could. Not wrong if you wrote it. Now the mass of that empirical formula, adding up 2 carbons, 3 hydrogens, and 1 oxygen, is 43.05 grams per mole. Now if we take the 2 masses and divide them, big one divided by small one, we see that there is an integer of 2. That integer is the relationship between the empirical and the molecular formula. So the molecular formula is going to be 2 times the empirical formula. C4H6O2. There you go. Now, another way of determining empirical formulas is through what we call combustion analysis. And for combustion analysis, it's very similar to what we've been dealing with, looking at the moles and trying to figure out the smallest whole number ratio for everything. But what a combustion analysis, why it looks slightly different, is because you have an unknown that you are reacting with oxygen gas to form carbon dioxide and water. Now, when you do this in the lab, you do it in a very different type of system. I have an image of that system later on that I'll show you. Normally, we don't do this in the lab simply because the system itself is not a closed system. You're not making a bomb, but in general, we don't often like to have explosions going on in our general chemistry lab. But when we do this, we get very, very important data. Namely, the data that we get are the masses of our products. So what's interesting about all of those masses that we know, the carbon in the product always comes from the unknown. The hydrogen in the product comes from the unknown. So usually what we have for this unknown is called a hydrocarbon. It's a hydrogen and carbon containing compound. So what we get to do with this is start to identify a couple of different things in this setup. So for instance, here would be the data question. A hydrocarbon is combusted in the lab to produce 1.83 grams CO2 and 0.901 grams H2O. Determine the empirical formula. We could also do the molecular formula if we had the molar mass. We'll just stick with the empirical formula. Now, a couple of extra steps here. We need to convert the moles of each, or convert the grams of each of these compounds to moles of the compound using their molar masses. However, we don't want the moles of just carbon dioxide. We want the moles of carbon. And for every molecule of CO2, there is 1 atom of carbon. So there is a 1-to-1 mole ratio. That is the value that we would like to have. So when we're looking at this, the one extra step in combustion analysis is the idea that we are using a molecular formula for carbon dioxide and water. But we still want to get down to the atomic level of moles, not of just CO2. We want to go further and get it for carbon itself. Same thing with water. There are 18.02 grams of H2O for every 1 mole of water, and there are 2 moles of hydrogen per 1 mole of H2O. That one's a tricky one to remember, so don't forget that 2 subscript in H2O tells you there are 2 hydrogens per 1 of water. Again, we take the smallest one, divide it. There's 1 carbon and 2.4 hydrogens. Now again, we can't convert that or round it, but what's really helpful is this chart right here. That 0.4 can't be rounded. These are just very, very helpful charts to remember. It's a multiple of 5. It's actually, if we think about 2.4, it's actually 12 over 5 in its fractional form. So what we would want to think about is carbon to the 1, H to the 12 over 5. If we multiply this by 5, we'll get the whole number ratio, C5H12. This chart is in your textbook. It's very, very helpful so that you can remember or start to recognize the fractional subscripts and know what to multiply by. Why we are multiplying by 5 is because it's a multiple of the 5th. 12 over 5 is 2.4. You can think about this is 1 over 5, 2 over 5, 1 over 4, 1 over 3, 1 over 2, 2 over 3, 3 over 4, 4 over 5. So what you're looking at there is just different variations of those fractions in decimal form, what we usually get out of our calculator. So be very aware, all of those denominators are what you are going to be multiplying by to get rid of the denominator. Excellent. So there is our combustion analysis. There are more complicated styles of questions. We're going to do those in class. However, what this basis allows us to do is start to see how we can manipulate the moles and manipulate masses and data from the lab in order to find empirical and molecular formulas. And I did say I would show you the combustion analysis setup. There's usually a lot of valves that go along with this. So oxygen, pure oxygen, is brought into a very sealed container so that it doesn't blow up. And that's where your sample goes, your hydrocarbon or your unknown. Now, when this is burned up, all the gas particles are funneled through different types of absorbers, a water absorber and a carbon dioxide absorber. Any leftover air that was also in this container in the furnace with the sample is then pushed out. The mass of H2O, the H2O absorber and the carbon dioxide absorber before and after the analysis is then taken so that you can see the difference in the weight. And the difference in the weight will be the amount of water or the amount of carbon dioxide. So that's a real life experiment with combustion analysis to develop or to investigate an unknown compound's empirical formula. Thank you all for joining.